Hello everyone, this is Aman Abdi, a final year PhD student at Swinburne University of Technology, Australia. Today I will present our work on maximizing the vertex coverage for top t-Bicliques in bipartite graph. I will firstly introduce the preliminaries of our problem and provide a formal definition for the same. Then we move on to the various techniques to solve our problem, where we discuss the baseline approach, fast greedy approach with and without index, and then our novel heuristic techniques and algorithm to address the problem. Lastly, I will present some experimental results on the real-world dataset and conclude the presentation. We start by defining a t-Biclique as follows. Given a bipartite graph G, a t-Biclique is defined as a bipartite complete subgraph of G induced by the vertex sets X and its neighbors n of X, and the number of vertices in X is equals to T. We distinguish a t-Biclique representation from other bicliques with a circumflex or a caret symbol over the vertex set. That is, for a t-Biclique with vertex set X and its neighbors n of X is represented as X with a circumflex. In figure 1, we show three t-Bicliques, namely x1, x2 and x3 with the circumflex, and then we further define a t-Biclique set coverage, where we firstly select a set of t-Bicliques with threshold on the U side denoted with x in Latin along with a circumflex, and define the corresponding coverage on the vertex set V as the union of all the neighbors of the consisting t-Bicliques. Then the size of t-Biclique set coverage is defined as the number of vertices in the coverage of this set of t-Bicliques. Next, we discuss some examples for better understanding of the t-Biclique set coverage. Let us consider two Bicliques, that is x2 and x3. Their corresponding vertices are inscribed within the dashed polygon, blue and green, as shown in the adjacent figure. Now we can observe that the t-Biclique set coverage for x2 and x3 contains v3, v5, v6, v7 and v8 with the total t-Biclique coverage size of 5. In contrast, for the set of t-Bicliques with x1 and x2, the t-Biclique set coverage contains v1, v3, v4 till v8, that is, the total size of set coverage is 7, which is greater than that of x2 and x3 since there is less overlapping. Now we define the problem statement for our paper, which is, given a bipartite graph G, a threshold T, we find the set of t-Bicliques such that the number of t-Bicliques in the set is K and the t-Biclique coverage is maximized. We now move on to discuss some of the real-world application scenarios for our problem. Two of the real-world applications are, first, creating K courses with T units. Given a student like unit bipartite graph, many a times due to the resources limitations of a department, finding K courses that most students like is more interesting and suitable for this kind of application scenario. Second, hiring collaborative research groups for a project. So finding top K collaborative groups, maximizing the topic coverage in a research expertise topic bipartite graph engulfs the range of research topics for such groups so that all the objectives of our projects are addressed and it becomes successful. We now discuss the challenges and contributions for the problem. The three major challenges faced for the problem are, first, exponential space complexity, since the straightforward greedy approach has to store all the enumerated t-Bicliques, which is impractical for the large datasets as the number of t-Bicliques requires exponential space. Second, reducing the unpromising t-Biclique enumeration, where for any two t-Bicliques with individual large coverage, they may collectively cover very few extra vertices. As such, how to effectively avoid enumerating only one is indeed challenging. On the other hand, some t-Bicliques inherently have small coverage and avoiding their enumeration is also challenging. Third one is the hardness of the problem. Although the greedy approaches quickly provide a guaranteed result for the problem, the worst case time complexity still remains exponential and could be impractical for the large datasets. We then provide our contributions addressing the challenges. The first one is we study the we study and formulate a new problem for enumerating top k t-Bicliques, which maximizes the coverage of one vertex set of a bipartite graph. Second, a fast greedy approach with index with an approximation ratio of 0.25. And next, we also proposed a new RT core ordering, which also forms the basics for our novel polynomial heuristic approach to address our problem. We now discuss the straightforward approach to address our problem, that is the baseline approach. It is adapted from the k-cover problem, where we firstly enumerate all the possible t-Bicliques and store them in the memory. Then we select k t-Bicliques among them iteratively. In each iteration, a t-Biclique with the maximum coverage over the remaining vertex set V is selected. The resulting algorithm requires exponential time and space complexity. We also apply some pruning techniques using alpha-beta core subgraph to prune some unpromising vertices based on their degrees. Since the baseline is the straightforward adaptation, it has several limitations such as enumerating unpromising t-Bicliques, exponential space complexity, and unpromising vertices. To tackle such limitations, we provide the fast greedy approach. Before introducing this approach, we first introduce some preliminary definitions, that is, private coverage contribution and minimal t-Biclique. Given a set of t-Bicliques, the private coverage of a t-Biclique is defined as the exclusive set of vertices which are contributed only by the t-Biclique itself in the overall t-Biclique set coverage. For example, in figure 2, for the set of two Bicliques containing xa and xb, the private coverage of xa and xb are an empty set and the vertex v9 respectively. Further, the t-Biclique with the minimum private coverage in a given set is referred as the minimal t-Biclique. We now present the fast greedy algorithm to address our problem. In contrast to the baseline approach where we enumerate t-Bicliques and maximize the coverage separately, we now perform them simultaneously. During the t-Biclique enumeration, we only maintain k t-Bicliques in the memory and update the top k t-Bicliques by replacing the minimal t-Biclique if applicable. We perform the replacement of minimal t-Biclique if the resulting coverage is more than 1 plus 1 by k times of the previous coverage. This condition has also been adapted across various set coverage problems. We also provide an example as follows. In figure 3, let there be a set of two Bicliques, say xa and xb with k and t equals to 2, where xa would be the minimal t-Biclique and the size of the t-Biclique coverage as 3. Let xc be the newly enumerated t-Biclique. So based on the required condition, the new coverage would be 5, which is greater than 1 plus 1 by k times of the previous one, which was 4.5. Hence, the maximum coverage by the fast greedy approach is 5. The fast greedy approach also provides an approximation ratio of 0.25. We observe that this approach requires only polynomial space complexity instead of exponential as in baseline approach. Although the fast greedy approach is quicker than baseline, the required time complexity is still very large and is impractical for the large datasets. Therefore, we now propose an online index to further improve our fast greedy approach. The SM index is an online index which is proposed to reduce the computation time of computing the coverage and minimal t-Biclique from the scratch. It mainly provides the following three features for the current set of top k t-Bicliques. First, it preserves the private coverage of each t-Biclique. Second, it computes the minimal t-Biclique, and third, maintains the t-Biclique set coverage. Moreover, we also ensure the introduction of SM index does not affect the approximation ratio and the overall time complexity. However, it does require some extra space to provide such features. Now, although the SM index introduced provides some efficient operations, the overall time complexity still remains exponential. Therefore, due to the hardness of the problem, even the fast approximation algorithm with an index cannot scale to the large datasets, and hence we now propose novel polynomial time heuristic approach to address the problem. The framework of the heuristic approach is based on the 4 carefully designed heuristic rules, which are as follows. we propose heuristic 1 and 2 to firstly ensure the generation of promising t-Bicliques, that is t-Bicliques with larger individual coverage. Next, we propose heuristic 3 to create multiple sets of top k t-Bicliques where each t-Biclique is generated using heuristics 1 and 2, and select the group with maximum coverage. Lastly, we introduce heuristic 4 following the idea of minimal t-Biclique replacement across all the multiple sets of top k t-Bicliques created using heuristic 3. Now it is obvious that generating t-Bicliques with larger coverage would find the required results earlier. To achieve this, a naive approach is to order vertices by their degree in non-ascending order and then generate t-Bicliques by the ordering. However, a vertex U with a high degree may have two hop neighbors, all with low degrees. Hence, this ordering cannot ensure the early generation of large coverage t-Bicliques. Therefore, we propose a novel measurement for each vertex on the U side denoted by RT core number. We firstly introduce an RT core, which is defined as the maximal connected subgraph of G in which all the vertices have degrees at least R and T in the vertex sets U and V respectively. Further, the RT core number of a vertex U is the largest value of RT such that U belongs to that RT core. Once the RT core number is defined, we may move towards the heuristic rules. We propose heuristic 1, which says for any two vertices U1, U2, if RT core number of U1 is greater than that of U2, the coverage of t-Biclique containing U1 may be more promising than that of a t-Biclique containing U2. Therefore, we order the vertices in non-ascending order of their RT core number. Once the vertices on the U side are in the RT core order, we then propose heuristic 2 to include the new vertex in the current vertex set X, leading to form a t-Biclique with potentially large coverage. Heuristic 2 is formally defined as follows. For a given vertex U, another vertex U prime is considered having higher potential to form a large coverage t-Biclique together with U if U prime satisfies the following constraints. First, it should appear after U. Second, it should be a two-hop neighbor of U. Third, it should have the highest RT core number among all the vertices satisfying 1 and 2. And lastly, the resulting Biclique set coverage should be maximized. Now utilize an example to compare the RT core ordering and non-ascending ordering of degree with respect to the size of the t-Bicliques generation. From figure 4, we observe that forming a two-Biclique with the top two highest degree vertices, that is U5 and U2, results in a coverage of two vertices, that is V5, V6. In contrast, forming a two-Biclique with top two highest RT core number, that is U6 and U7, results in the coverage of three vertices. Since heuristics 1 and 2 cannot guess a t-Biclique with maximum coverage, and it is highly likely that we may encounter several t-Bicliques with the maximum coverage turn up to the time, to address this, in heuristic 3, we create a new top k t-Biclique set whenever we find a t-Biclique with the maximum coverage with respect to the t-Bicliques generated till now, and thus maintain several sets of top k t-Bicliques. Further, we also introduce heuristic 4 inspired from the fast greedy approach to update all the sets of top k t-Bicliques by replacing their respective minimal t-Biclique wherever applicable. Now we present the heuristic algorithm where we firstly sort the vertices using the RT core ordering. Then for each vertex U, we generate a large coverage t-Biclique using the heuristics 1 and 2. Next, if the generated t-Biclique is having the maximum coverage, we create a new top k set of t-Bicliques using heuristic 3 and also check whether the generated t-Biclique can update any of the top k t-Biclique sets according to the heuristic 4. Eventually, we select the set with the maximum vertex coverage. Now, the proposed heuristic algorithm requires only polynomial time and space complexity. For a better understanding, we then move to discuss some examples for the heuristic approach. For this example, let K and T be 2. For the given bipartite graph in figure 5, we start by performing RT core ordering of the vertices. The first two Biclique generated are x1 and x2 according to the heuristics 1 and 2. The overall coverage of the set containing these two Bicliques is 3, that is V7, 8 and 9, with x2 as the minimal 2 Biclique. Next, x3 is generated and is eligible to replace x2 in the current result with size of the updated coverage as 4 and x3 as the minimal t-Biclique. Similarly, x4 is generated and replaces x3, consequently providing the result as the set of x1 and x4 with the coverage size of 5 vertices. Note that the algorithm still generates t-Bicliques, however they cannot satisfy the replacement condition and hence are incapable of updating the current result. Now, although heuristic algorithm provides a good coverage, also evident from the later experiments, it does not provide any approximation guarantee, and therefore we integrate our heuristic algorithm with the fast greedy approach to provide an approximation guarantee. Since we know that larger the coverage of top t-Biclique set is, the better pruning effectiveness is. Therefore, the result obtained from the proposed heuristic approach serves as the lower bound result for the fast greedy approach. Moreover, we also integrate the RT-core based pruning to remove the vertices, which makes the coverage of any t-Bicliques containing it very small without affecting the time complexity and the approximation ratio. We further explain pruning with the help of an example. In this example, we firstly recall the results of the heuristic approach containing the two Bicliques x1 and x4 with the set coverage of 5 vertices and x4 being the minimal t-Biclique with the private size coverage of 2. Now integrating the RT-core based pruning with the fast greedy approach, we observe none of the vertices satisfy the threshold. That is, none of the vertices can produce a t-Biclique which can beat the minimal t-Biclique with respect to the private coverage size. Hence, we obtain the result quickly along with the approximation guarantee. Now, this concludes the theoretical contribution for the paper, and we now provide the experimental analysis for our proposed approaches. We evaluate our experiments across 5 real datasets by utilizing different settings of the query parameters t and k. For all the datasets, the value of k is selected from 10, 15, 20, and 25. And the value of t can be 3, 4, 5, and 6. We evaluate the efficiency and effectiveness by varying k with constant t equals to 5 and varying t with constant k equals to 15. We also evaluated the effectiveness of the 4 heuristics proposed. With respect to the efficiency from the shown figures, the baseline is the slowest among all the algorithms, followed by the fast greedy approach. Both of them are unable to provide results within the cutoff time for the large datasets. As expected, the heuristic algorithm outperforms all the other algorithms across all the instances. Moreover, in contrast to the fast greedy algorithm, the improved greedy approach provides results quickly, and sometimes it is comparable to that of the heuristic algorithm, implying the effectiveness of our RT-core pruning. We now observe the effectiveness of each algorithm by comparing the size of the resulting t-Biclique coverage. We observe that the baseline always provides the best coverage, which is also evident from the approximation ratio. However, it is impractical for the large datasets. On the other hand, we also observe the coverage of the fast greedy and improved fast greedy is comparable. In addition, the improved fast greedy approach provides results for the larger datasets, which is not the same for the fast greedy approach. Although there is no approximation guarantee for the heuristic approach, we observe that its coverage is comparable to that of improved fast greedy approach. Apart from the individual algorithm evaluation, we also provide the analysis of the proposed heuristic rules. We utilize the incremental evaluation approach resulting in 4 heuristics and observe that the incorporation of all the heuristics is more likely to provide a better coverage than the partial combination of the heuristics. To conclude the presentation, I would like to say we studied the new problem of top t-Biclique coverage in bipartite graphs. We proposed a novel heuristic approach with 4 heuristic rules based on the proposed RT-core number. The heuristic proposed can also serve as a reasonable standalone algorithm, as well as it can be extended to serve as a lower bound for pruning vertices and improving the performance of adapted greedy algorithm significantly. Thank you.